What if I told you that there's a single, simple rule that underpins all of physics? I mean, a hidden principle that governs everything, from how a planet orbits the sun to the weird flicker of a quantum particle. Well, it turns out there is. And the story of how we found it is one of the most incredible tales in all of science.
So our journey to find this ultimate rule, it doesn't start with spinning galaxies or quantum weirdness. Nope. It starts with a surprisingly simple problem that completely stumped the greatest minds of the 17th century. A problem all about finding the most efficient path.
All right, picture this. You've got a ball and you want to get it from a high point, let's call it A, to a lower point, B, using a ramp. The question is, what shape should that ramp be to get the ball there in the absolute positively fastest time? This is the famous brachistochrone problem, which basically just means the problem of fastest descent.
Now, your first gut instinct, probably my first instinct too, is a straight line, right? It's the shortest distance after all. But it's not the fastest. See, if you make the ramp steeper right at the beginning, the ball gets this huge burst of speed early on. So even though it ends up traveling a little bit farther, its average speed is so much higher that it gets to the finish line first. The real question is, what is that perfect curve?
Galileo himself actually took a crack at it. He guessed it was a simple arc of a circle, but he was wrong. So decades go by, and in 1696, a mathematician named Johann Bernoulli throws this thing out there as a formal challenge to the entire world. Eventually, the problem makes its way to Isaac Newton. He gets it after a long day working at the Royal Mint. He's annoyed, but he's also intrigued. He sits down to work on it and solves it in a single night. By 4 a.m., he had the answer. Just incredible.
And here's the best part. Newton, being Newton, submitted his solution anonymously, but his genius was just unmistakable. When Bernoulli saw it, he famously said, "I recognize the lion by his claw." He knew there was only one person on the planet capable of a solution that powerful and elegant. But here's the twist. While Newton's solution was this incredible act of pure mathematical force, Bernoulli's own solution was, you could argue, way more creative. He found the answer not by wrestling with mechanics, but by looking at a completely different field of physics, the behavior of light. You see, Bernoulli was a big fan of the work of Pierre de Fermat. Fermat had figured out why light bends or refracts when it goes from, say, air into water. And he realized light is basically an optimizer. It doesn't take the shortest path. It takes the path that gets it where it's going in the least amount of time. You could say the universe is the ultimate shortcut finder.
And this is where Bernoulli has his lightning bolt moment of genius. He thought, hang on, what if the falling ball is like a ray of light? As gravity pulls on the ball, it speeds up. He imagined this was just like light passing through different layers of a material that get less and less dense, causing the light to speed up and bend continuously. He realized the math describing both situations was exactly the same.
So by using the laws of how light refracts and applying them to a problem about gravity and motion, Bernoulli found the equation for the perfect curve, and he knew it instantly. The fastest path isn't a straight line, it's not a circle, it's a cycloid. The exact curve you'd get if you tracked a point on the edge of a rolling wheel. I mean, what an absolutely mind-blowing connection between two parts of the universe that seem to have nothing to do with each other.
This powerful idea that nature seems to be, optimizing for something really stuck with one of Bernoulli's students, a guy named Fermat and Maupertuis. He started wondering, maybe Fermat's least time for light was just one small piece of a much deeper, much more universal principle playing out everywhere. So, in the 1740s, Maupertuis came up with a new quantity he called action. He had this intuition that nature is just inherently economical. He defined action as an object's mass times its velocity times the distance it travels. And he claimed that for any process, nature will always pick the path that minimizes this total amount. He called it the true expense of nature.
So, how did the world react to this grand unifying idea? Oh, it was a disaster. Absolutely terrible. He got accused of plagiarism. The famous writer Voltaire, apparently holding a personal grudge, wrote a vicious 32-page pamphlet just to mock him and his idea. And scientifically, people just dismissed it as kind of vague, arbitrary, and not mathematically sound. Poor Maupertuis died thinking his greatest idea was going to be completely forgotten.
But his idea didn't die. It was rescued and completely transformed by two of the greatest mathematicians who ever lived, Leonhard Euler and a young prodigy named Joseph Louis Lagrange.
They saw that spark of genius in what Maupertuis was trying to say, and they set out to give it the rock-solid mathematical foundation it deserved.
So together, they totally redefined what action even means. It's not that simple mass times velocity times distance formula anymore. In its modern form, action is the total of a system's kinetic energy, that's the energy of motion, minus its potential energy, that's the stored energy, all summed up over the entire journey. That one value, kinetic minus potential, is so important that it gets its own special name, the Lagrangian. Okay, so how does this actually help? Well, the goal is to find the one single path, out of all the infinite possible paths an object could take, that has the minimum total action. The method they developed basically uses calculus to find that one special path where tiny little wiggles to either side don't change the total action. Think of it like this. If you're standing at the absolute bottom of a valley, taking a tiny step in any direction doesn't really change your altitude. That's the spot nature is looking for.
And when you grind through all that math, when you find that bottom of the valley path, it spits out a single, powerful master equation. And what happens when you use that equation on a simple system, like a ball flying through the air? You get F equals ma, Newton's second law of motion. It's the same thing. This incredibly deep, abstract idea about minimizing something called action is just a more fundamental way of describing the same laws of motion we already knew. It's just staggering.
This was a total game changer. The principle of least action wasn't just some weird mathematical curiosity. It gave us an entirely new and often much, much more powerful lens to look at the universe with.
All of a sudden, physicists had two different toolkits to solve any problem in mechanics. You had the old Newtonian way, which is all about forces and vectors, all the pushes and pulls, and now you had the new Lagrangian way, which completely ignores forces and just looks at energy, a single, simple number. For really complex systems, the Newtonian approach can become a tangled nightmare of vectors. But the Lagrangian approach, it's often shockingly simple.
And this new method is just unbelievably powerful. If you want to figure out the chaotic motion of something like a double pendulum, it's a total headache with Newton's laws, but it's pretty straightforward with the Lagrangian. It works in any coordinate system you want, and it basically acts like a machine. You figure out the energies, you plug them into the master equation, you turn the mathematical crank, and out pop the correct equations of motion. It's almost like magic. Now, one quick little clarification. We've been calling it the principle of least action, and that's the common name. But to be super precise, it's really the principle of stationary action. Nature is just looking for a path where the action is at a flat point. That could be a minimum, yeah, like the bottom of a valley, but it could also technically be a maximum, like the peak of a hill. For most of the systems we deal with every day, though, it does turn out to be a minimum. So this one elegant principle ties together classical mechanics, optics, and as physicists would find out later, it's right at the very heart of both relativity and quantum mechanics too. It seems that at its deepest, most fundamental level, the universe is constantly solving an optimization problem, always finding the path of stationary action. Which leaves us with a pretty profound question, doesn't it? Why? Why is the universe so efficient? And what does that really tell us about the fundamental fabric of reality itself?